When we left off, I was in the process of reconstructing 70s and 80s computers on an FPGA, something which I a priori knew nothing about. As I started, I found out that something which I took for granted I actually don't have, and that's a 6502 CPU. Most of the computers from that era were using the 6502 CPU, and one is really needed in order to reconstruct it. I was hoping to use one of a couple of open source projects implementing the 6502 in HDL, in hardware description languages, but turns out I can't use either one of those. I'm not sure what the problem is or where it is, but when I tried to input those into the project and use them, things didn't work. So I said, well, how hard can it be? I'll do it myself. Right? I mean, how hard can it be? For the past 2 weeks, that's pretty much what I've been doing. I've been writing a 6502 CPU in hardware description language called Verilog, in a development tool called Vivado, which is Xilinx's development tool for the Spartan 7, which is what's on this board here. And it's been coming along fairly well. I mean, we have here a list of all of the opcodes the 6502 has. And there are, count them, 1, 2, 3, 4, 5, 6, more or less 212 opcodes, of which I've implemented at this point 14, which is looking good, right? But I'd argue that this is actually further along than it sounds. To understand why, let's look at those opcodes in a little more detail. So we see, for example, that opcode number 1 is OR A, which means OR the accumulator, with an operand that comes from taking the 0 page, adding X to it, and then using that in an address to where the actual number is. But then operand 11 in hex is again OR A, but this time we take the 0 page, treat that as a number, as an address, and then add Y to that address. And 12 is OR A, just taking a 0 page address and using that as a pointer to where the address is. Furthermore, we see 05 is OR A, just an address in 0 page, and so on. So we see the same operand appears in several areas here, and it does the same thing except for where it gets the data from. Then again, if we look at 31, we see AND. So unlike OR, this time we are ending the accumulator with a number, but we take it the same way we took 11. So we use a 0 page address, dereference it, and then add Y. So we see that the operations we're performing repeat themselves, but so do the addressing modes we're using. So in effect, we can sort of put this in a table where we'd have the addressing modes on the columns and the operations on the rows, and we'd get a different view into the same 212 opcodes. And what do you know? Such a table actually exists. We can see here exactly what I just said. So we have here the operations to perform. It continues on the next page and the page after that, and all the addressing modes. So instead of 212 opcodes, we can say that we have 98 operations and 16 addressing modes. The question is, why would that help us any? But if we look at the 14 opcodes I've already implemented, so we see I've implemented load A in absolute absolute plus X, absolute plus Y, immediate addressing, 0 page plus X indirect, 0 page plus X, 0 page indirect, and 0 page indirect plus Y, then yeah, I mean, I did only 14 commands. Hey, I've got no operation. I did that as well. So 15 commands. I may have only done 15 opcodes, but I've covered most of the addressing modes. And if I can build the code so that I can somehow separate the two, then maybe I'm further along than it first seems. And to understand that, let's look at the block diagram of the CPU. And what we see is that data arrive here on the data bus, and the CPU is divided into two parts. The right part is called the control section, and the left part is called the register section, but can also be referred to as the data area. So the data resides here, the user data, and this part here gives control lines onto how the data should be manipulated. And we see that the data bus, which obviously arrives to the data area of the CPU, also gets picked at, and this error is actually in the reverse direction. It's in the wrong direction. I actually let Western Design Center know about this, and they said they'll fix it in the next version of the datasheet. We'll see. But we see that the data, when it comes in, enters this something called instruction register. And what the instruction register does is it keeps a copy of the opcode around for the decoder section to use later. And there is one more thing to note. This here is called the timing control. And what this does is it keeps track of how long have we been inside this particular opcode. So essentially, we have the opcode and we have the cycle counter of the opcode, and these two are the state of execution right now. So these two completely determine what are we supposed to do at this point. Sure, that's the WD65C02S, so that's a very specific version of the 6502. But if we look at the design for the original 6502, we see the exact same thing here. Here the directions are reversed. The right side is the data area and the left side is the control area. But still, we see the data bus going into the instruction register, and we see the timing generation logic both controlling the control logic. So it's the same despite this diagram being much more detailed than the more modern diagram. So let's have a look at how this translates to actual code. Let's open the decoder. And what we see here is, first of all, we have the timing counter, which is the timer control. Since the longest instruction I found in the 6502 takes about around 6 cycles, I gave the timing counter 4 bits, which means it can count from 0 to 15, and that ought to be enough for any opcode executed. We'll see if that's a problem later on. And what we see is that when we get a clock, specifically when we get the negative edge of the clock, so the falling edge of the clock, we check the timing counter. First, we check the reset line, assuming the reset is high, which means we're okay to execute. We check the timing counter. And if the timing counter is 0, it means that our data in this variable contains the opcode. Now, it sounds trivial. I wrote rewrote and rewrote this code multiple times before that became as true, as confidently true as I'm saying it right now. But let's move on and just assume that's the case. So if timing counter is 0, then data in contains the opcode, which means we're going to a function called do opcode decode, which is here, which unsurprisingly looks like a huge case. So case data in. If it's 0, then the instruction is break and the addressing mode is ADDR stack. If it is 1, then the instruction is OR accumulator and the addressing mode is 0 page plus X indirect. If the instruction is 4, because 2 and 3 are undefined, then the instruction is test and the addressing mode is 0 page and so on. Of course, these aren't implemented yet. But if we move down to the area where I did implement things, which takes a while because there are a lot of commands, let's move to this area. So we see that A0 is load Y and the addressing mode is immediate. And two below that, A2 is load X and the addressing mode is also immediate. So what we see here is that I managed to create this orthogonal design where we handle the addressing mode and we handle the operation, and the two are done independently. To understand how that's done, we need to have a look at these two variables. One holds the active address resolution type and the other holds the active operation. So essentially, when we receive a new opcode, instead of just storing the opcode in the instruction register, what we do is we split it into this is the operation, this is the addressing mode, and we store them in two separate registers. To really understand how that works, let's just add a new command right now. Let's go with load X from absolute address. That's opcode AE. So the first thing we need to do is find AE in our huge case. And we see it here. So first thing is first, we just uncomment it. Now, pretty much we're done, at least in theory. But we really want to make sure that's actually the case. So ideally, what we would like to do is run something that triggers this command. In order to do that, we need to simulate the entire CPU. Thankfully, Vivado has exactly such a thing. It works like this. You write code in Verilog that simulates whatever you want. So in our case, we just feed it a clock and we make sure the clock works the correct way. And then we feed it a sort of memory image and the CPU can work off that memory image. And when we actually run it, it looks like that. I'm going to skip a single clock each time. And right now nothing happens because the reset line was low. But now reset line goes up. And what we see is that we're asking the address bus of 0 and we're getting back EA as the value in address 0. EA is the opcode for NOP, no operation. And at this point, we're starting to execute. So we see the sync line going low. The sync line is an indication the CPU gives that tells us that we are on the fetch instruction of a next command. So The sync line is the CPU's way of saying, I'm fetching an opcode now. So the sync line goes low. The timing counter switches to 1. Well, it switches to 8, but we'll talk about why later. And the address advances even though no operation obviously doesn't need the next address. Now, moving forward another clock, we start fetching the next instruction over, which is at address 1. So the address remains at 1, the sync goes back high, and now we've fetched the next opcode, which is also EA, so another no operation. And again, one cycle when we do nothing because this is no operation. And then another fetch from address 2. So this is the third memory cell. And again, it's EA. And again, we do another cycle where we do nothing. The next fetch returns A9. A9 is load A immediate. Now, what we see next is that the address advances to 4. And indeed, we read the value to read in, which is 3. But next, what we see is that the A accumulator, the accumulator register, receives the value 3. So we see the command actually got executed in 2 cycles, which is good because that's how long it takes on the 6502. And the 6502 got the sync line back up in preparation for fetching the next instruction over, which is A9, another load A immediate, and so forth and so on. So if we want our new command, the one we just implemented, AE, load X absolute value, we want to test that it does the right thing, what we need to do is put that into the simulator's memory. Now, the simulator memory is read from this file, which contains what needs to be done, and it also contains a bunch of addresses we use to, let's just fix this, a bunch of addresses we use in order to read or write relevant values. So what we need to do is, we're here at address 37, that was the last command. We can now add another command, which is AE, and let's document what it is. So that's load X from address 61A8. Now, the way this is encoded is after the opcode, we have 2 bytes of operand, which tells us the address with the least significant byte first. So that would be A8 followed by 61. And to give it some slack to see that things actually happened, we're going to follow that with another no operation. So EA, that would be at address 3, 9 plus 3 is 12, which is B. And we've placed a NOP. Next, we need to place at address 61A8 the value we want to be read. Now, throughout this file, what I did is that the value being read is the address from which the command ran. So we need to go to 61A8 and place there the value 39. So that's our test bench, and we can run it. Go to the simulator, ask to reload everything, and then run to completion. I'll talk about what that means in a second. And we are at, our next read is from address point 39, which is exactly where we placed our address, our new command. And indeed, we get AE on the data line. And if everything goes right, this will end as register X receiving the value 39. So let's see. First cycle is the fetch. Second cycle, we read from 3A the value A8. And then we read from 3B the value 6.1. And now the moment of truth. We read from 6.1 A8 the value 3.9. And register X gets the value 3.9, and we're on to the next instruction, which is a no operation. So we just tailored the two parts that we needed, and lo and behold, this worked. When we placed the correct instructions in memory, our CPU, or at least CPU simulation, correctly executed them. But it's a bit tedious to run this manually each time and make sure each time that the command runs that it takes the correct amount of cycles. It's a lot of work. And it would be nice if we could do that automatically. And guess what? We can. Again, I had to write all of this. Well, at least all of this. So what I have here is a file that reads out as the expected run, how the test is supposed to pan out. And the first 4 bits, so everything here are multiples of 4 bits, so that I can write this in hexadecimal, and everything, and there will be no half digits. So the first digit says what type of line this is. Right now, just 3 are supported. 0 means opcode with immediate values. So this is an opcode that doesn't touch the actual memory in any way. 1 means this is an opcode that performs a read in some form. And 2 means this is an opcode that performs a write. So, and now the second digit is the number of cycles this command should take. So if we go to the 6502 datasheet, we can see that the amount of cycles each command should take is almost only dependent on the addressing mode it uses. Now, the new command we added uses the absolute addressing mode, so it should take 4 cycles, unless it's a read, modify, write command, such as add or XOR, which has to read the value, compute the new value, and then write it back. So that adds 2 cycles. But load X is not a read, modify, write command, so just 4 cycles. That's how long it should take. That's on the 65C02. On the original NMOS 6502, it also took 4 cycles. And the command itself is 3 bytes long. Again, no changes there. With that in mind, we can now go here and say this. This is a read command. It should take 4 cycles. The opcode is AE. It should be read from address 39. The last data being read is supposed to be 39, and it should be read from 61A8. And while we're at it, the next command is an immediate command. It has to take 2 cycles. Its opcode is EA. It should initially be read from 3B. This value doesn't matter because it's an immediate command. And the last address bus should be at 3C. So we've just added that into the test bench. And before we run that, let's insert an error. Let's give it the wrong cycle count. Now, when we go to the test bench, we say reload and just run. And what we have is an assert failure. And if we use the call stack, we see that the failure is here, opcode shorter than expected. If we go to the test bench, we see that it actually carried out our instruction in full, but then it started the next instruction and our test bench said, well, sync shouldn't have come up for one more cycle. And that failed the test. So let's go back to the memory and put in the correct cycle count. And now if we load, we see that the test, well, we failed, Let's see why we failed. Command read from wrong address. Let's see. It read from 3C and we told it that's the NOP. And we told it it will read from 3B. 9ABC. Yeah, that was a mistake in the test plan. So let's reload. And what we see is that we ran 32 events successfully, and therefore the simulation stopped. And if you're wondering before why the simulation stopped right as we got to our command that we added, the answer is it wasn't in the test plan yet. But now it is in the test plan, so we verified everything. We know everything works. We know we haven't broken anything, at least not in any way that matters. And we've successfully added the new command, and frankly, we spent much more time on making sure the command was tested than on actually implementing the command. So, like I said, I'm hoping this will greatly reduce the amount of work I have on implementing all 212 opcodes. The CPU isn't ready yet in other respects. There's so far no support for the flags, the carry, negative, etc., and no support for interrupts. But otherwise, everything is in place. Right now, this needs 203 LUTs, lookup tables, out of the 8,000 we have. I expect this number to grow significantly because the way the case here is implemented is heavy user of LUTs, but still I'm hopeful this will remain a fairly small number. We'll see. It also uses 116 flip-flops. This number I don't expect to increase significantly because those are for storing state between cycles. So I don't think that would be a problem long run. So we'll see. And I will join you next time as I report progress and hopefully show you other cool stuff I've done. Thank you for watching.